Good afternoon, and welcome to Data Structures. Today we're going to talk about a couple of things here. First of all, some of this is a little review. So you may recall in class we talked about something that I refer to as the insertion loop. Then we're also going to talk about something called the insertion sort. And then finally, we're going to talk about something called analysis of algorithms. And this is going to be something that's very important. It's going to come back for every data structure and every algorithm that we look at. And what we're going to do is we're first going to discuss analysis of algorithms with regard to the insertion loop and the insertion sort. Now, just a little bit of review here. You may recall that the insertion loop looked something like the following. We said we had some array here. We said that part of the array was already sorted, so maybe it looks something like this. And we have some number x here, and this is at 0, 1, 2, 3. The name of the array is called AR. And what we wanted to do is we wanted to insert this into this subarray. Okay, we basically wanted to insert AR of 3 into the sorted subarray. Remember, we made up this notation. We said that AR from 0 to 2, such that after we insert it, that the subarray from 0 to 3 is sorted. And we came up with the following loop for doing this. We said something like the following. For j is equal to 2, while j was greater than or equal to 0, j minus minus. And we said something like the following. If AR of j, oh, we did something else here too. We did something like the following. We said let temp equal AR of 3. So then we said if AR of j is greater than temp, break. Is that correct? Did we say if AR of j is greater than? I think that's incorrect. I think we wanted this the other way around. Let's get rid of that. Oops. Okay, if AR of j is less than temp, break. Otherwise, what we want to do is we want to say let AR of j plus 1 equal AR of j. And that's the end of our loop. And then the tricky part, we argued about this in class, we want to say let AR of j plus 1 equal temp. Okay, so this thing over here, this is what we call the insertion loop. And we noted a couple of things here. We considered several things here. We said suppose that x is less than any of these elements. Suppose x was equal to 6. Did this work? And the answer is yes. Then we considered the case, what if x is bigger than any of these? Suppose x was equal to 99. Does this loop work? And the answer is yes. And then the other thing that we said is well, what if x is some number in between here? Like, what if x is 45? Does this loop in here work? And the answer is yes, it does. So we're pretty confident in the correctness of this loop. So we wanted to generalize this a little bit. And we said, well, all right, so now we have an array from 0 to 3. What happens if I want to insert this element over here at 4? And we said, well, that wasn't too hard. All we need to do is just change this to a 4, and we would change that to a 3. Okay? So I hope that this is clear for everyone. What I want to do now is I want to do a little bit of analysis of this algorithm. And a lot of times when we analyze the algorithm, we want to consider a couple of cases. And sometimes you want to consider what's the best case. Best case meaning in what situation will this algorithm do the least amount of work. And the other one you want to consider is what is the worst case. And then the really hard one is what's called the average case. Okay, now let's consider what do I mean by the best case. Well, the best case means what is the fastest way for this algorithm to terminate? Well, the fastest way for this algorithm to terminate is if I go ahead and I do this assignment here, I come in here to this for loop, and now when I get down here, that this Boolean condition turns out to be true. Because if this Boolean condition turns out to be true, I immediately do the break. I jump down to here, I insert the thing, and I'm all done. In other words, I don't have to cycle around in this loop from j. I don't have to do it for j equals 2, for j equals 1, and for j equals 0. I just have to do it for j equals 2. So if this is going to be true the first time that I come into the loop, this is going to be the case where x is greater than 47. Okay, so the best case would be x is greater than 47. And what I want to do here is I want to actually count things. So if I count things, I'm going to come over here and I'm going to do an assignment statement here. Okay, so this statement I would do once. And then what's going to come in here to do this thing, I'm going to assign j equal to 2. Okay, and then what's going to happen is I'm going to see is j greater than or equal to 0. Okay, and that's true too. So remember, I do the assignment, and then what happens over here is I check this thing here. So what I'm doing here is I'm executing 2 instructions. Now the way to think about this is you might want to think back to your computer science 221, when what would happen here if this was actually in machine language. And again, you can see there's an assignment statement, and then over here we're somehow testing a Boolean condition. Now I'm going to come down in here, okay, and it says if, over here I'm doing a comparison, and when I do the comparison, that's an operation, and I'm doing the break, and that's also 2. And then what happens is I come down here and I'm doing an assignment statement. And when I do the assignment statement, that's doing a 1. Now this is very informal, but I think you'll see where we're going. So if you come over here, we actually did 1, 2, 3, 4, 5, 6 operations. Okay, and that's the best case. Now, what would the worst case be? The worst case would be, of course, if I never execute the break statement, I have to keep going around and around and around in the loop. I finally exit it, and then I come down here. So the worst case would be if x is less than 12. So if x is less than 12, let's figure out what's going to happen. Well, first, let me erase all of this. And it's not erasing. That's going to erase it now, I think. No, it's not. We're having a technical difficulty here. Just excuse me for a moment. All right, I think we have our technical difficulty figured out here. So let me erase these numbers from before. And now let us do the worst case situation. Now in the worst case situation, remember we said that that occurs if this number x is actually less than 12. I'm still going to come over here and I do the assignment, and that's going to take me 1. Okay, I'm going to come over here and I do the assignment. Okay, so I do the assignment j is equal to 2. And I come over here and I say, is j greater than or equal to 0? And that is, so that's going to give me 2. I'm going to come down here. If a of j is less than temp, that's going to be false, so that's going to be a 1. I'm going to come over here and do this assignment here. That's going to be a 1. Then what's going to happen is I'm going to come back up here, and now I'm going to do a j minus minus. Okay, that's going to make j a 1. And j, I'm going to do the Boolean expression again. J is greater than or equal to 0. So that's another 2. I'm going to come over here, and I'm going to look at this Boolean expression again. It's going to be false. That's going to be another 1. I'm going to come over here, and what's going to happen is I do another assignment statement. That's 1. I'm going to come back up to the top. I'm going to subtract 1 from j. J is now 0, which is still greater than or equal to 0. So that's another 2 operations I did. I'm going to come over here. This statement over here is still false, so I don't do the break. That's another 1. I'm going to come over here. I'm going to do this statement. That's another 1. I'm going to go back up to the top. When I go back up to the top, j goes down to -1, and this is now false. But I have to count those operations. And now I'm going to come down here, and I'm going to do this over here, this assignment statement. Okay, and so finally, when the j got less than 0, we had to come down here, and we had to do the assignment here. So this took 1. And if we come over here and we add all of these up, so I get 1, this is 2, 4, 6, 8, that's 9, 10, 11, 12, 13, 14, 15, that's 16 operations. Okay? So in one case, 6 operations, in one case, 16 operations. Now you might wonder about the average case, and I have to tell you that calculating the average case sometimes can be extremely difficult. And we're not going to do it. We're just going to worry about the best case and the worst case. But now, what happens here is I want to consider a more generalized version of this thing. I have some array here. It looks like the following. And let's suppose it's a big array. And it goes all the way up to n-1. It's called AR. So there are a total of n elements. And whereas before we assumed that we wanted to insert the third element, now what I want to assume is I want to assume that I have some arbitrary element at position k. And I want to assume that the array from AR from 0 to k-1 is sorted. And what I want to do is I want to insert this into the sorted array. And what I'm going to do is it's going to sort of look just like the last algorithm as before. I'm going to say temp is equal to AR of K. And now what I'm going to say is I'm going to say for J equals K minus 1, while J is greater than or equal to 0, J minus minus, and I'm going to come in here and I'm going to say if AR of J, and let's remind ourselves how we wrote it last time, if this is less than temp, then what I want to do is break. Otherwise, I want to let AR of J plus 1 equal AR of J. And I'm going to come down here and end this. And down here, I'm going to say let AR of J plus 1 equal temp. Okay? And again, I'm calling this, this is what we're calling the insertion loop. And what I want to do now is I want to do a best case and a worst case analysis of this. Now, if I'm going to do the best case, the best case analysis would be that that X is bigger than any element in AR from 0 up to K minus 1. And we can see that if we're going to do that, then what I have to do is I'm going to come over here, and this is going to be just like the other one. I'm going to come over here, and I've got to do one assignment here, and I've got to do one assignment here, and I've got to check one Boolean expression. So there are 2 over there. Okay? And I'm going to come over here, and this is going to be true, and that's going to be true. So I'm going to do 2 over there, and I'm going to jump down here, and I'm going to do an assignment, and that's 1, and I'm all done. And I'm going to say this takes 6 operations. And that's just like before. Okay? And now we're going to do the worst case. And the worst case is going to be X is smaller than all elements in AR of 0 to K minus 1. Okay, so let me come over here and erase what we've written up here. All right, so let's pay attention here. First of all, we know that we're going to do this once. And we know that we're going to do this once. Okay? What about this statement over here? How many assignment statements are we going to do here? Well, in other words, remember what this statement here is doing. It's taking this element and moving it down to here. It's taking this element and moving it down to here. This element here and moving it down to here. This element here and moving it down to here. So what's basically going on is if this is going all the way up from 0 all the way up to K minus 1, okay, and we're going to be moving this to here, and this to here, and this to here, and this to here, and this to here. How many elements are we moving in general? Well, again, we can go back here, and we can see that in our other one here, we were doing that, in this one we had to do this a total of 3 times when we were going all the way up to the 3rd element here. So that would suggest to me that over here, I am doing this K times. Okay? Now, likewise, what about this here? Well, in the worst case situation, remember, I never actually execute the break, but I'm going to be doing this how many times? Well, again, I come over here and I can see I'm doing it 3 times. I did it here when this was 3. That would suggest to me that I'm going to be doing this k times. And now over here, remember what happens. I'm doing assignments and comparing to the Boolean once, and then what happens is I'm doing decrements and I'm doing the Boolean once, and I'm going to do that k times, but then there's also the time where it gets down to -1. So this is going to be 2 times k plus 1. Does everybody see that? Okay, remember here k was 3, k plus 1 would be 4. I did 2 times k plus 1. So over here, it's going to be 2 times k plus 1. Okay, so if I come over here and I add these up, it's going to be 1 plus 2 times k plus 1 plus k plus another k plus 1, and that's equal to 1 plus 2k plus 2 plus k is another 2k, and then plus 1. So that's 4k, 4k plus 2 plus 3 plus 4 plus 4. So in the best case, we are going to do this 6 times. In the worst case, we're going to have 4k plus 4 operations. Okay, so let's consider a little bit of what we just discussed here. So we said that this insertion algorithm, this insertion loop, right over here, we said that in the worst case scenario, if I'm at position k in the array and I want to insert that into the subarray, in the worst case, it's going to take 4k plus 4 operations. Now, one could make a couple of arguments about this, why this is inaccurate. They may say, well, on this particular machine, it may have been 4k plus 4, but on different machines, maybe these things get combined into a number of different operations. And you're right. So we may do a different analysis, and in another analysis, it might turn out to be something like 4k plus 17. And we might do another analysis, and in another analysis, it might come out to be, 10k plus 89. But here is the point that I notice. The point that I notice is I have a loop that basically looks like this. It goes for j equals k minus 1, while j is equal to 0, j minus minus. And there's some stuff inside of here like this. Now, why don't we make the stuff inside here really simple? Why don't I just put a system.out.println hello. And the question, here's my quiz question for you today. How many times does hello print out? And the answer to that, well, it goes from 0 to k minus 1. That's k times. Well, I want you to compare this k with what we got over here. We had a 4k plus 4. And we argued, well, maybe it could have even been some other numbers. It might have been 10k plus 89. It might have been 56k plus 1002. But the point 56k, the point that is in what's important here is notice that in all of these answers, the biggest variable we had here is we had a k to the first. And when we're analyzing algorithms, that's really the only thing that's important. We don't care about these constants, because these constants might be different from one machine to another. They might be different from one computer scientist to another computer scientist. And in fact, these constants that are in front of the k really don't matter either. And I'll explain that in a moment. But what is important is that when we talk about the complexity of this algorithm, if I were to say to you, what is the worst case complexity of this algorithm, you would say that it's order k. Or sometimes you hear people say it's big O of k. Or people will write it this way. They'll write a big script O like that, and they'll say k. They'll say big O of k is equal to k. So here's the thing here's the important takeaway from all of this, and that is the following. Let me create another page here for it. Okay. The big takeaway here is that it was k and not k squared or k cubed or k to the fifth. And the reason why these constants really don't matter is because we want to consider when k gets arbitrarily large. So let me give you an example. Suppose I have algorithm A, and suppose I have algorithm B. And both of these do the same thing. But I go ahead and I count the operations in these things. And algorithm A takes 1,000 times k to do something. And algorithm B takes 0.001 k squared. And the question that I have for you is in general, which algorithm is better? Well, you got to be careful here. That's a little bit of a loaded question. For example, if k is equal to 1, we can see that this would be 1,000 and this would be 0.001. So let's consider, we could even make a table here. Here's k, and here's algorithm A, and here's algorithm B. And if k is 1, then A is going to take 1,000, and B is going to take 0.001. And in that case, clearly algorithm B is better. But what happens if k is, say, 100? Well, if k is 100, then what's going to happen is algorithm A is going to take that long, which is 100,000, and B is going to be 0.001 times, let's see, what is 100 squared? Well, that's going to be 10,000. Okay, and we can see that algorithm B is still much faster than algorithm A. But what happens here? Well, let's consider the following. Suppose k is 1,000,000. Now when I come over here and I look at algorithm A, that's going to be 1,000,000 times 1,000, that's 1 billion. Sorry, those things are getting pretty small. And if I come over here, and this is 1,000,000, now things are starting to look a little bit different. Okay, so first of all, if it's 1,000,000, this is going to be 1,000,000 squared, so that's 10 to the 7th squared. That's equal to 10 to the 14th. But then what I have to do is I'm going to divide it by 1,000. That's equal to 10 to the 11th. So this would be 10 to the 11th. And we can see at this point, this is 10 to the 9th, this is 10 to the 11th. This is getting bigger. So in fact, if k is equal to 1,000,000, algorithm B is bigger. And we can see now that as k gets even bigger than that, algorithm B is going to take longer. So the point is that we come over here, and over here we would have that big O of k is equal to k, and over here we would have that big O of k is equal to k squared. And we would say that as k tends towards infinity, algorithm A is the faster algorithm. Now for specific numbers and for k pretty small, algorithm B is faster. But as k gets bigger and bigger and bigger, algorithm A is clearly superior to algorithm B. So when we're talking about this stuff, there are a couple of different names for this. This is sometimes referred to as the time complexity. This is sometimes referred to as the analysis of algorithms. It's sometimes referred to as the runtime complexity. And we will use these terms interchangeably. Okay? So I want to finish up this discussion here. And we talked about this in class. Remember, we have this insertion loop that looks something like this. We say let temp equal AR of k, and then we said something like the following. We said for j equals k minus 1, while j is greater than or equal to 0, j minus minus, and then we came in here and we said if AR of j is less than temp, then we said do a break, otherwise do AR of j plus 1 is equal to AR of j. And down here we said let AR of, what did we say down here? AR of j plus 1 is equal to temp. Okay, so this was called the insertion loop, but then we said, hey, suppose we have an array called AR that goes all the way from 0 up to n minus 1. And we said, why don't we stick this whole thing in here inside of a loop, and we come over here and we say for k equals 1, well, k is less than or equal to n minus 1, k plus plus, and we come in here and we do that. Okay, so we're executing this inside loop, the insertion loop, for k equals 1, for k equals 2, for k equals 3, all the way up to k equals n minus 1. Well, remember, what this whole thing is doing is this is sorting the array. And whereas the inside of this thing is called the insertion loop, this whole thing here is referred to as the insertion sort. And now I want you to think about the following. I want to think about what is the complexity of this entire loop right here. Okay? Well, this isn't as hard as it looks. Remember that each time I execute the inside loop, we said that the thing is of order k. And what's going to happen? K is equal to 1, k is equal to 2, k is equal to 3. So The inside loop, the first time that we go through it, it's of order 2, and then it's going to be of order 3, and then it's going to be of order 4, plus 5, plus, and it's going to go all the way up to n minus 1. Okay? In other words, the first time I execute the inner loop, k is 2, and k is 3, k is 4, k is 5, k is all the way up to n minus 1. So the question is there any way that I can express this number? And the answer is sure. And what I need to do here is I need to show you another very clever little trick. And this is a trick that is due to the great mathematician Gauss about 500 years ago. And the question is suppose I wanted to find out what is 1 plus 2 plus 3 plus all the way up to some number n. Let's call it n right there. And what I want to do is I want to call that s. And what I'm going to do is I'm going to rewrite s, but now I'm going to write it in reverse order. So it's going to be n plus n minus 1 plus, like that. I've just, in this line here, I've just written this in reverse. And now what I want to do is I'm going to add them up. So this plus this is 2s. Well, this is equal to n plus 1. And this 2 plus n minus 1, that's also equal to n plus 1. And I keep adding these all the way up over here. That's n plus 1. And the question is how many of these are there? And the answer is there are n of them. So I get the 2s is equal to n plus 1 times n. And s is equal to n plus 1 times n over 2. How cool is that? So if I want to know how much is 1 plus 2 plus 3 plus all the way up to 10, by this formula over here, that's equal to 11 times 10 over 2 is equal to 55. How cool is that? Okay, so we just need to finish our analysis for the insertion sort. And remember, we said that insertion sort, if we started counting things, we got 2 plus 3 plus 4 plus all the way up to n minus 1. This was assuming that we had an array with n elements in it. Well, if we look at this formula over here, we know that 1 plus 2 plus 3 plus n is equal to 2 times n plus 1, or I'm sorry, not 2 times that. It's n plus 1 times n over 2. So if I subtract 1 from both sides, I get 2 plus 3 plus n is equal to n plus 1 times n over 2, and this would be minus 1. Well, this thing should only go up to n minus 1, and this one goes up to n. What I certainly could do is give myself a little more space to write. I'll say OK. Let me come over here. So what I need to do is I'm going to just transpose this. I have that 2 plus 3 plus n is equal to n plus 1 times n over 2, and this is minus 1. And now I get 2 plus 3 plus n minus 1 plus n is equal to n plus 1 times n over 2 minus 1. And now I'm going to subtract n from both sides. 2 plus 3 plus plus n minus 1 is just equal to n plus 1 times n over 2 minus 1 minus n. So I want to come over here and I want to simplify this expression right here. So first of all, that is going to be equal to n squared over 2, and that's going to be plus n over 2, and that's going to be minus 1 minus n. So what I would like to do is just be able to combine terms, or I can make the following note. Notice that here I have a polynomial. This is just 1/2 n squared. Okay, I'm going to go n over 2 minus n. That's going to be minus n over 2 minus 1. And again, using our observation before that we really don't care about the constants or anything lower here. The important term is this thing right over here. So in this case, we would say that big O of n is equal to n squared. Or we would say that the time complexity of insertion sort is n squared. And you may recall that we said a while ago that we're going to be looking at what are called the elementary sorts. And the reason why they're called elementary sorts is because they all have a time complexity of n squared.